Hello, welcome to this lecture. In the last lecture, we have defined a regular surface. So in this lecture, we'll give more examples of regular surfaces embedded in three-dimensional space, R3. Okay, so let us begin. So before going to give more examples, so let us again recall the definition of a regular surface in R3. Yeah, so let us take S subset of R3. So this is my three-dimensional space. And we have some set like this. So this is my, say, S. So S is a regular surface. So if for all P belonging to this S, so if I take any point P in this S, so I can find an open neighborhood of this point P in the whole space R3. Something like this. So this is this open neighborhood of P in R3 is, I call it to be B. So if for all P belongs to S, so there exists an open neighborhood B of P in R3 and a map sigma U to B intersection S. Okay, so this is my say U here. So this is in R2 and I have a map sigma. So sigma land inside this B and sigma of U is equal to B intersection A S. Okay, so a map sigma such that so this U, it is an open set in R2. So such that so this sigma is differentiable at all points of U. Second thing is that so the sigma is a homeomorphism onto its image. Okay, and the third thing is so the sigma is differentiable. Okay, means that the differential of the sigma exists for all points of U. So sigma differential implies the differential of sigma exists for all points Q in belonging to U, and so this differential map is injected. Okay. So if we can cover this S by this pair uh, P comma B such that so these conditions are satisfied, so then we call S to be a regular surface. Okay. So now, so just let me define what do you mean by surface patch. So the pair, so U comma sigma is called surface patch. Okay. And now also note that, so this S, so this is in fact, it is union of sigma of U. So, so sigma is varying over all. Okay, so sigma, maybe I'll write like this. So for each point, P in S, so I have this B and U and this map sigma. Okay. And now if I vary this P, so this U will vary, sigma will vary. So I'm varying those sigma. Okay. So I'm not writing here. So if I vary those sigma, so S is union of all this sigma U. Okay. All right. So in the last class, we have shown that a sphere, in sphere it is a regular surface. Okay, so we have used one parameterization. So here we'll use another kind of parameterization, means another type of surface patch we'll choose. So example. So again, let us take unit sphere. Okay, so now we'll decompose this S2 into union of two open sets. Okay, so how to get those open sets? So let us take this unit sphere. Okay, and now you take the north pole, which is 0, 0, 1, and also you take the south pole. Okay, and you take S2 minus north pole, so you delete the north pole, and B to be, or let us take maybe I'll just U1 to be S2 minus N, and U2 to be S2 minus the south pole. Okay, so this U1 and U2, so this are sets in the sphere. Okay. 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 So this U1, so this you can think as also as the following. So if you take B1 to be R3 minus the north pole, so U1 is basically B1 intersection the sphere S2. Okay. And Similarly, if I take this B2 to be R3 minus the south pole, so this U2 is B2 intersection the sphere S2. Okay, so this B1 and B2, so these are my open sets in, so B1, B2 are open sets in R3. Okay, all right, and also observe that so this S2 is equal to U1 union U2. Okay, so I have this thing here. So now, so I need to find the surface patches corresponding to this U1 and U2. Okay, so in order to get the surface patch, so there is something called stereographic projection. Okay, so what is stereographic projection? So you take the line segment starting from this north pole. So it will intersect the sphere, and if you continue, so it will intersect this XY plane. Yeah. So suppose this point is my XYZ. So I'm taking the straight line starting from this north pole. It will intersect the sphere X in XYZ and intersect the plane in capital X comma Y comma 0. Okay. So now, so what will be my coordinate of this point? Capital X and capital Y in terms of this small xyz. So this is called stereographic projection. Okay, so you are projecting from the point North Pole. Okay, so from the equation of the straight line, so what you can write, so x by capital X equal to y by capital Y equal to z minus 1 by minus 1. Okay, so this will imply that x by capital X equal to y by capital Y is equal to 1 minus z. Okay, so therefore, so this capital X is nothing but x by 1 minus z, and capital Y is y by 1 minus z. Okay, and also you have this relation x square plus y square plus z square equal to 1. And here note that so this z is not equal to your 1. So x square plus y square plus z square is equal to 1, and x here is capital X multiplied by 1 minus z whole square plus capital Y multiplied by 1 minus z whole square plus z square. Okay, so from here, so you'll get a quadratic equation in z. You can solve that thing, and because z is not equal to 1, so what you'll get, so this so z, so this will be equal to x square plus y square minus 1 divided by x square plus y square plus 1. Okay, and so therefore, so this x, so x is given by this, so x is equal to capital X times 1 minus z. So you can put the values of z here. So what we'll get? So x is equal to 2x divided by capital X square, capital Y square plus 1. And similarly, small y is 2 capital Y divided by capital X square, capital Y square plus 1. Okay, so now I can take sigma 1, a map from R2 to your U1. So what is my map? So sigma 1 of uh, capital X comma Y. So this is equal to 2x divided by x square plus y square plus 1, 2y by capital X square, capital Y square plus 1, comma capital X square plus capital Y square minus 1 divided by this. Okay. So again, so check that. So sigma 1 is a homeomorphism, differential map, differentiable map, and d sigma 1 at each point xy is injected. So this you can check. And similarly, so if I define sigma 2 from R2 to U2, so how you'll get this thing? So let me draw again this sphere. So earlier we have taken stereographic projection from the North Pole, and now what we are doing, so we are taking the stereographic projection from the South Pole. So you take the straight line coming out of the South Pole like this. So it will intersect yeah. So again, it will intersect the sphere at one point and then the plane at this point x comma y comma 0. Okay, so the sigma 2, so capital X comma Y, so this you can compute. So what you'll get is twice x by x square plus y square plus 1, twice y by x square plus y square plus 1, comma 1 minus x square minus y square divided by x square plus y square plus 1. Okay, so again, so this map sigma 2 is again, it is a homeomorphism, it is a differential map, and d of sigma 2 it is injective, differential is injective. So so therefore, so what we got, so we got this two surface patches. So R2 sigma 1 and R2 sigma 2 are two surface patches, and sigma 1 R2 is U1 and sigma 2 R2 is U2. Okay, so we got this thing. So therefore, this S2, it is a regular surface. This unit sphere is a regular surface. Okay, all right. So so now let us give another example. So you take right circular cylinder. So x, y, z in R3 such that x square plus y square equal to 1. Okay, so this is cylinder. So yeah. So if I take this map sigma ub to be equal to cos u sin u b, okay, so this sigma, so this will give you a surface patch. Okay, so this is the hint to prove that C is a regular surface. Okay. Okay. So now, if I take this cone, if I take this cone, yeah. So if I take this cone, so this is not a surface. Why it is not a surface? Because if I take this point, if I take this point, if I take any neighborhood of this point, it will be something like this. So if I take any neighborhood of point in the surface, it will be something like this. So it is never, so it is not homeomorphic to uh, an open subset of R2. Okay, so why it is not homeomorphic to an open subset of R2? So suppose there exists a surface patch u comma sigma such that sigma u is equal to, so let us call this to be my w, equal to your w. Okay, and yeah, so so this is, you can take it to be connected, so you can chosen to be connected. Okay, and there exists q belongs to u because it is a homeomorphism. So there exists a unique point. So there exists a unique point q belongs to u such that sigma of q is equal to this point P. Okay, and so W minus this point P is disconnected. Okay, so while or whereas this U minus P is connected, and sigma of u minus p is equal to w minus, okay, so this will be u minus q, so w minus p. So u minus q is connected and w minus p is disconnected. So this cannot be possible. So this is a contradiction. Okay. So therefore, so this thing, so this cone, it is a not a surface. Orbit. Okay. Okay. So now let me give you the definition of smooth surface. So a regular surface is said to be smooth if for all surface patches u comma sigma, the map sigma is a smooth map. Okay, so that is all the partial derivatives of sigma exist up to desired order and they are continuous. Okay, so this is the definition of smooth surface. So whatever we deal with, so most of the surfaces, almost all the surfaces will be smooth on. Okay, all right. Okay, so now in order to get more examples, so let us prove this proposition. So let us take a different real value differential function defined on an open subset of R2. So if f is a differentiable uh, differentiable function defined on an open subset U of R2. So then the graph of f, okay, so what is this graph of f? So graph of f, so this is defined to be x comma y comma fx y, where this xy is varying in u. So this graph of f, so this is a regular surface. Okay, so how to prove this thing? So proof. So let us take, so let sigma xy to be equal to x comma y comma fxy. Okay, and so this map, it is a, so sigma is a differential map, and homeomorphism onto its image. Okay, so now, so what will be the differential of this map? So d sigma evaluated at the point xy, so this will be a linear map from this R2 to R3. Okay, so what will be the matrix of this linear map? So matrix of this linear map, so this is equal to, yeah, so yeah, so it is the, so first we have to take the, okay, so recall that, so sigma xy, so if this is f x y g x y h x y, okay, so then, so the matrix will be, so you take the partial derivative of f with respect to x and partial derivative of f with respect to y, similarly for the other coordinates. Okay, so here fxy is just x, so therefore first row will be 1 comma 1 0, second row will be 0 1, and the third row, so h is here this f, so here I should write, let us call it to be u. I have already used this f, so let us call it to be u. And h is here this f, so this will be my, the partial derivative of f with respect to x, partial derivative of f with respect to y. So this will be the matrix of d sigma at the point xy. So the rank of this matrix is 2. Is 2. So therefore, so this linear map is injective for all xy belonging to u. Okay, so therefore, so this implies that, so this graph of f is a regular surface. Okay, so therefore if I, so if the graph of f is something like this, so if I take any point xy here, so coordinate of this point will be x comma y comma fx y. Okay, so this is a regular surface. Okay, okay, so we'll stop here, so we'll continue in the next class.